Okay, we're at the very last section to be covered in the semester. Finite difference methods for two-point boundary value problems. The announcements I have here are the same as before. I need each and every one of you, all 14 of you, to contact me and let me know how you want to handle the final. Also, I've for some of you, I have not received any homework lately. I know I've been very lenient on homework submission even before the pandemic forced us to go online. Um, but again, it's not just because of not wanting to have everything dumped on me at the end of a semester, but I am concerned about the lack of submissions from some people. So if you're having difficulty keeping up with things because of what's going on, I urge you to please contact me. I cannot help you if I don't hear from you. So and hopefully all of you are at least watching this video. Um, and remember, uh, Thursday of finals week, May 14th, so that's 2 weeks from this Thursday. That's the last day that I'm able to accept work and have it graded in time for submission. Um, okay, now, um, review the problem that we're dealing with in this chapter, two-point boundary value problem. Y double prime is this function of x, y, and y prime on a bounded interval AB. These two boundary conditions are imposed. So we've seen one approach to solving this kind of problem of a shooting method for both a linear and nonlinear case. Today we're looking at a very different approach, finite difference methods. Um, Today we'll look at linear problems and also some convergence analysis in general. And then on Monday, um, the last lecture that I'll record will be on finite difference methods for nonlinear problems. The coding option for the final deals with these boundary value problems, either shooting method or finite difference methods. Okay, so I need to lay down some notation to describe a finite difference method. Um, so the idea here is um, we compute the solution, um, the approximate solution, which will have this form, y1, y2, yn. So whereas the exact solution is a function y of x, our approximate solution, the computed solution, will be a vector of capital N values, where each yi is an approximation of the exact solution at some point xi, and I'll define xi now. X of I is equal to um, a, the left endpoint of your interval, plus ih, and h is equal to b minus a over n plus 1. We actually saw this quantity for in the case of the uh, shooting method. Um, so, um, so all of these points. Okay, let me fill in the indices here. Okay. So all of these xi's are interior points. They do not include the endpoints because we already know the solution at the endpoints. It's equal to alpha at the left endpoint and beta at the right endpoint. So if we have endpoints in the interior, that requires n plus 1 subintervals in the interval AB, and so therefore they would have this width. So we have this equal spacing of these points. Okay, now let's see. So to discretize the BVP, we replace derivatives, the two derivatives involved, y double prime here and y prime here, finite difference formulas. So finite difference formulas we'll be using. We have various choices, but here are the most commonly used ones. So, multi-line, multi-line equation. So first, y prime at a given point. Actually, I put equals because I'll include the error. So the actual approximation is a centered difference. So yx I plus 1 minus yx I minus 1 over 2h. So that's the centered difference. And then the error in that this finite difference formula is squared over 6 y triple prime at some unknown point a to I, which I'll define momentarily. And then the second derivative also a center difference. So we have h squared down below, and then up top we have y xi plus 1 plus 2y xi. Okay, plus y xi minus 1. Okay, so that's a center difference formula for a second derivative, and then the error was also order h squared. So we could use more points to get higher order accuracy, but that would also make a method less efficient. Okay, and both these derivatives are evaluated at unknown points. So what we can say about those unknown points, we know they belong to the interval from xi minus 1 to xi plus 1. Okay. So now what we can do is use these finite difference formulas, substituting them into the boundary value problem in place of these derivatives here. So what does that give us? All right, so and here I'm also going to use the approximate solution. So what I'm also going to do is I'm going to take this f, move it to the left side, so then we'll have 0 on the right side. So my equation will be for each I from 1 to n. Because what I'm going to do is I'm going to evaluate these derivatives, this whole equation, at each interior x, and we have n of those points. So at each xi, what I will have is f evaluated xi, yi, and I'm going to have my approximate y prime here. That'll be the center difference, yi plus 1 minus yi. And over here on the left, I need my approximation of the second derivative, so I'll fill that in. Okay, so now this is a boundary value problem just isolated on one side. Both derivatives replaced by the respective finite difference formulas. Now I'm going to abbreviate this. So this whole expression here is, you can think of it as an operator, LH, applied to the vector y, and then I'm taking the ith component of that vector. So LH of y is a linear operator applied to the vector y that computes this expression for each component, for each I, using the values in y. So we want each component of LH of y to be equal to 0. So what this gives us is a system of equations so linear or nonlinear, depending on whether the boundary value problem is linear or nonlinear, a system of n equations in the n unknowns, y1, y2, up to yn. Okay. So system of n equations, y1, y2, yn. Now, one thing I need to point out, though, is let's suppose I is equal to 1. If I fill in I equal 1 in here, so first component of this vector, LH of y, then I'll have y2, okay, minus y1 plus y0. But I've defined y for indices 1 up to n. I don't have y0. Similarly, if I have I equal n, I'll have y n plus 1, also not defined. But we can define those using boundary conditions. Y0, that is the exact solution at x naught. X naught would be just a. And we know what it is. That's alpha. Whereas y n plus 1, that is equal to y at x n plus 1. Now, if I fill in I equal to n plus 1 here, I would just get b. So that's y of b. And we know what that is. That is beta. All right. So when I is equal to 1 or n, we need to include the boundary values in these equations. But those are known, so that's not a problem. Okay, so now we need a way to solve this system of equations to get the values y1, y2 up to yn. But how that's done depends on whether the problem is linear or nonlinear. So I'll get to that shortly. But first, what I want to do is talk about concepts that we solve for initial value problems that have natural analogs in boundary value problems. A local truncation error, and what it means for a method for a boundary value problem to be consistent. And one of the homework problems in this section does deal with local truncation error, so it's important that I say something about that. Okay, so now, what is local truncation error? So the local truncation error of a finite difference method has a simple definition in terms of the notation already given. So I'll use tau I of h, this similar notation was used for local truncation error for initial value problem. We used the letter tau, and n referring to the index of a time step. Here we're looking at I. We're using I, the index of the grid point in space. So it's local truncation error defined at each particular point at which the solution is computed, and it depends on the spacing h. So in that sense, exactly the same idea as for initial value problems. And another similarity, it is obtained by substituting the exact solution into the numerical method. Okay. Now, I need to give some notation here. Let x be a vector consisting of all of the x values. Oh, I need to fix this. All right. Okay. So now, so if x consists of the vector x consists of all the grid points that we're using. Then we're plugging in all those points into the exact solution. So I'll make that clear here too. Just as we always used to refer to y of t as the exact solution of initial value problems. Same idea. So local truncation error is obtained by substituting the exact solution at all the grid points into the numerical method, and then we take component I to get component I of the local truncation error. So local truncation error is really a vector valued quantity. It's defined for at all the grid points. Here I'm just showing you how it's defined for a particular grid point. So now I will write out or type out what that is. Um, so it's defined for I going from 1 up to n. Okay, so let me fill in the particulars here. So we have xi, y of xi, so the exact solution evaluated at this x, and then the finite difference approximation of the first derivative, okay, and then same thing for the second derivative out here. Hopefully I have room for all of this. Okay, so this is the exact solution substituted into the numerical method. Now, the computed solution, when substituted in here, will have all of this equal to 0. But with the exact solution, there will be something left over, and that something is the local truncation error. And I need to make a note here that x naught, because x naught will come up in this case when I equals 1, that is equal to a, and x n plus 1 is equal to b. So again, so the boundary values can be taken into account when I equals 1 or I equals n. So since this is meant to be something that's small, and should go to 0 as h goes to 0, so we say the method is consistent. Okay. So I should say the local truncation error of the finite difference method defined above. Okay. Now, so I want to emphasize what I described above right here. This is one choice of finite difference method. For this finite difference method, this is a local truncation error. Okay. Now, if I have a different finite difference method, if I substitute the exact solution into it, then I would have a local truncation error for that method. So the method is consistent if tau of h goes to 0 as h goes to 0. Well, that's it a whole 18 or 19 minutes or so before the recording cut out. Let's see if I can get through the rest of this. All right, so this is a local truncation error for the above finite difference method. If the local truncation error goes to 0 as h goes to 0, when we say the method is consistent. And this has to be the case. This has to be the case for I going from 1 to n. All right. Now I want to make this discussion a little more general. So in general, tau of h is obtained by, as I said earlier, substituting y of x into I should say y of vector x. So evaluate the exact solution at all the interior grid points, and you substitute that into your method. And this definition applies for consistency. So if so for whatever method okay. So if you substitute the exact solution to whatever finite difference method you have, like for instance, what if we use a higher order finite difference for this second derivative or this first derivative? Then what you get is local truncation error. If that local truncation error goes to 0 as h goes to 0, then that finite difference method is consistent. All right. Now, one of the homework problems is to obtain an expression for local truncation error of this method. In other words, you want to determine, is it order h squared? Is it order h to some other power? Now, try to simplify it. So I realize the wording of a problem make you think, oh, you just give this. But no, you're supposed to actually work on this to try to get an idea as to how rapidly the local truncation error goes to 0 as h goes to 0. So to work out well, did not even get another 3 minutes before it cut out again. So to work out local truncation error, tau I of h, use Taylor expansion of the above expression around xi. So we're good. So you Taylor expand this whole expression around xi. And what that means is this expression here that I'm highlighting over h squared, that is the second derivative at xi, and that's worked out by Taylor expansion anyway. So you can include the error in this first derivative formula. Now, to get the error in this formula worked in, that's a little trickier. What you need to do is multivariable expansion of this expression, this evaluation of f, um, uh, around xi, y of xi, and y prime of xi. So if you Taylor expand this, so Taylor expansion of this whole thing around xi, which is a single variable expansion, would include multivariable expansion of its evaluation of f around xi, y of xi, y prime of xi. Now, the nice thing is f is already evaluated at these two coordinates of a center, so that simplifies things greatly. But you want to expand it around y prime, so that's where partial derivatives of f will come into play, as well as the error in this finite difference formula. Now, you have to, and this is true in general when evaluating local truncation error, you have to include that y of x is the exact solution at xi is equal to f of xi, y prime xi, in order to make your expression for local truncation error as simple as possible. So you get some cancellation from that. Okay, so local truncation error should be order h, like a power of h. right, because certainly if that's true, um, then the method will be consistent. The local truncation error would go to 0 as h goes to 0. Okay. So, um, so for completeness, the reason why we need multivariable Taylor expansion is if you're taking a Taylor expansion of this whole expression around xi, um, then you would need a derivative with respect to x of this whole expression um, evaluated at xi. But since this argument and this argument both depend on x, um, to take the derivative of this whole thing with respect to x, um, you would need chain rule, and that's why you need partial derivatives of f with respect to its other arguments. And that would amount to a multivariable Taylor expansion in a way. Okay, now the other thing is, if I were to expand this and this around xi, you could what would happen is if things would simplify to the point where you would see the see y double prime of xi appear. But to save you some time in doing that, what you can do instead, and I feel like I have to scroll very carefully, or the recording will stop again, is um, see this is already in your local truncation error, so you can replace this in the local truncation error by y double prime of xi minus this error term. So in other words, y double prime plus h squared over 12 fourth derivative of y. So that will save you a little time in your manipulations. Same thing for the first derivative. Okay. So that's all I have to say about local truncation error. There is a notion of stability for finite difference methods also, which is similar to that for initial value problems. I'm not really going to get into it here just because there's no homework problem on it. It's actually quite difficult to analyze compared to initial value problems. There's a lot more um, mathematical machinery involved with it. But it's a similar general concept that um, the method is stable provided that if there's a small change in the problem data, such as the boundary conditions, um, then that does not lead to a large change in the solution. And also, whatever change there is can be bounded independently of the spacing h. Again, just like for initial value problems. So, um, and just like for initial value problems, if a finite difference method is shown to be consistent and stable, then it is also convergent, meaning that the computed solution approaches the exact solution at the grid points as h goes to 0. Okay. All right. So oops, put that in the wrong place. Okay. So those concepts, it's not really very interesting. It just all works the same way as for initial value problems. Um, okay. Um, and how these concepts all relate to one another. It's all the same. Okay, now I want to talk about linear boundary value problems. Um, so we have y double prime is equal to some function p of x times y prime plus q of x times y plus r with the same boundary conditions. So then, okay. I'll check my notation here. All right, before I talk about how it's rewritten, minus y double prime plus p of x y prime plus q of x y is equal to r, and r is a function of x. Okay. So I'm just moving a y double prime to this side, the side of a p and q, and should be a minus here, and r of x is moved to the opposite side. Okay, so now if I replace y double prime and y prime with these same finite difference approximations, then what I get is, okay, so for second derivative, I would have y I minus 1 minus 2y I plus 1, or sorry, yi plus y I plus 1 all over h squared. But I have a minus out front, okay, and then I'll have plus p of xi, okay, and then the first derivative, 2h down below, and then y I plus 1 minus y I minus 1, okay, plus q yi is equal to minus r of xi. Now what I'm going to do is, actually, I've pretty much done my rearranging. I'm going to multiply both sides by h squared, and take into account of a minus. So I have minus y I minus 1 plus 2yi minus y I minus 1, or plus 1 rather, okay, plus h squared over 2 p of xi times yi plus 1, and I also have a similar term for yi minus 1. I'm going to put it to the left, just because I want the points ordered from left to right on the grid. Um, and then I have plus h squared q of xi yi is equal to minus h squared r of xi. Okay. Now, these equations are defined for I going from 1 to n to cover all the grid points. Okay. Now, the next thing I'm going to do I'm going to take terms of the same index of y, so yi minus 1 or yi or yi plus 1. I'm going to group all of those together. So first, yi minus 1. All right, so what's multiplying yi minus 1 up here? So I have a minus 1 from here. And then over here I have this. I have minus h squared over 2 p of xi. Okay. And then what is multiplying yi? Well, I have a 2 right here. Nothing here, nothing here. And over here I have plus h squared q. Okay. And then I will also have expression for yi plus 1. The only difference is here I'd have a plus instead of a minus. It'll be yi plus 1 is equal to minus h squared rxi. Okay. So the reason why I did this grouping is what I have here is a system of linear equations because the boundary value problem is linear. So it's basically an ax equals b problem. The right-hand side would be the b vector. What's on the left side would define the matrix. So whatever's multiplying, this is for I going from 1 to n. So whatever's multiplying yi, this is a diagonal entry. Whatever's multiplying yi plus 1 is a super diagonal entry. Whatever's multiplying yi minus 1 is a subdiagonal entry. So here we have the entries of a tridiagonal matrix. So I need to take into account equations that involve boundary values. So for I equals 1, right, so I'm going to make a copy of this. Actually, 2 copies of it. For I equals 1 and I equals n. So throughout this, I'm going to substitute I equals 1. And this would be y naught. But y naught is equal to alpha. And then here I have I equal 1. And then here I have, again, I equal 1. And then y2. And then x1. Okay, now this term right here, because it involves a boundary value alpha, that's already known. So that actually should go on the other side. So I'm going to move that to the other side. Okay, so I got to change the signs, so everything will be plus. Okay, so that's what we have for the first equation. So we have this boundary term on the right side. For the last equation, I equal to n. So I'll fill in I equal n throughout. And over here I have y n plus 1, but that is equal to the other boundary value, that would be beta. So now this term needs to be moved to the opposite side. All right, and I'm just going to take that minus and distribute it. Um, so here are the special cases of equations: the first equation and the last equation. Every other equation will have this form. Um, so um, so our vector of y values, system of solution of a system of linear equations, ay is equal to r, where the components of r are given by what's on the right side of these equations. So this is the first component, um, r1. This is the last component, rn, and every other component of r, ri, is given by this right-hand side. Whatever's multiplying yi are the diagonal entries. These are the subdiagonal entries. These are the superdiagonal entries. So A is tridiagonal. Okay. And it's worth mentioning if Q is positive, or at least non-negative. Now, which is actually, wait, greater than or equal to 0. It's actually, we like to have the assumption that df dy, which is Q, is not just non-negative, but positive, um, uh, to guarantee a unique solution of the original boundary value problem. And we have this condition: h is chosen small enough. Okay. So 2 divided by whatever maximum value of p of x is. Um, so we use the largest here to have a most stringent condition on h. Then we can say that a is um, strictly row diagonally dominant. Okay. So we can guarantee that it's not singular. It would be nice if we could say that A was positive definite, but we don't even have A being symmetric, let alone positive definite. But we would like to have some criteria for a solution of a system at least existing, having some sort of guarantee that A is an invertible matrix. So if the boundary value problem is well posed in the first place, and H is chosen sufficiently small, then yes, this system can be solved. Okay. Now, I want to refer you to example 13.2.2 for setting up um, and displaying solution of a boundary value problem. So it will rely on code that needs to be written for the homework. And actually, I think, okay, yeah, code is written for the homework that sets up a system of equations and solves it to compute the solution of a boundary value problem. So you'd be populating a diagonal, subdiagonal, superdiagonal with entries according to these formulas. So the code um, will, shown in this example, will show you how to set up like function handles for P, Q, and R, and for example BVP, where the exact solution is known, plotting the computed solution, plotting the exact solution, so that uh, you can compare them at least visually, um, and also plot the error. Um, okay, so that's all I have for linear boundary value problems using finite difference. So for my final lecture on Monday, I will discuss how we um, solve these kind of problems using finite difference methods in the nonlinear case, using a root finding method such as Newton's method, generalized to the case of a system of n equations in n unknowns. So please keep that homework coming in. Please let me know what do you want to do for the final exam. Please let me know, especially if you're having any difficulties getting the work done. So again, I can't help you if I don't hear from you. So um, hopefully I'll hear from you in some form, whether it's homework or just letting me know what's going on. Okay, till next time.